Introduction to Electrodynamics by David G. Griffiths, problem number 2.14. In this problem, we have to find E field inside a sphere that carries a volume charge distribution rho. And this distribution of charges is proportional to radius of sphere r, which means as we move away from center of the sphere, the distribution of charges increase respectively. So to find E field, consider a sphere on which charges are distributed, and the radius of this sphere is represented by capital R. We have to ask E field inside this sphere. So to find E field, we consider a Gaussian surface in the form of concentric sphere, and the radius of this sphere is represented by small r. Here concentric means two or more spheres have same center are called concentric spheres. As from figure, it is clear that for inside small r is less than capital R. So to find E field, we use integral form of Gauss's law, that is equal to according to integral form of Gauss's law, close integral E dot dA is equal to Q enclosed over epsilon naught. To make calculation more easy, we assume that this arrangement of charges is placed in a spherical coordinate system. Spherical coordinate system. We call this equation number 1. Here we have to find Q enclosed by this sphere that can be calculated by volume charge distribution relation, as volume charge distribution rho is equal to charge per unit volume, and from here Q enclosed is equal to rho into V. As in our problem, rho is not uniform because rho is proportional to R. As we move away from the center of this sphere, charge distribution increase respectively, which means volume charge distribution is not uniform. So to find Q enclosed by this sphere, we integrate this relation, as Q enclosed is equal to integral of rho v. We call this equation number 2. As we say, this arrangement is placed in a spherical coordinate system. So in spherical coordinate system, volume is equal to, in spherical coordinate system, we have v equal to d of tau, and this is equal to triple integral of r square sine phi dr d theta into d phi. So we put this relation into equation number 2, and equation number 2 becomes Q enclosed equal to triple integral of rho into r square sine phi dr d theta into d of phi. Here limit of integration for r, theta and phi is given as, for r, theta and phi is given as for r 0 to r, and for theta 0 to 2 pi, and for phi 0 to pi. So this expression is written as with limit of integration as Q enclosed is equal to triple integral of rho into r square sine phi dr d theta into d of phi. As discussed in previous slide, for r limit of integration is 0 to r, for theta 0 to 2 pi, and for phi 0 to pi. As from given problem, rho is proportional to radius of sphere. Here we take radius of Gaussian sphere, and this is equal to rho equal to k of r. We just put this value into this relation, so q enclosed equal to triple integral of kr cube sine phi dr d theta into d phi. Here limit of integration are 0 to r, 0 to 2 pi, and 0 to pi. First we solve integral due to r. First we solve integral due to r. So q enclosed equal to integral of 0 to 2 pi integral 0 to pi. Here we apply power rule of integration. So this will be k r4 over 4 into limits 0 to r and sine phi d theta d phi. So q enclosed equal to integral limit from 0 to 2 pi integral limit from 0 to pi k r4 over 4 minus 0 over 4 sine phi d theta and d phi. Here just we apply this limit into this expression. So this will be equal to q enclosed integral limits 0 to 2 pi integral limits 0 to pi and k r4 over 4 sine phi d theta into d phi. Now we solve integral due to theta. Now we solve integral due to theta. So q enclosed equal to integral limits 0 to pi k r4 over 4 sine phi into theta limits 0 to 2 pi into d phi. Here so q enclosed equal to integral limit 0 to pi k r4 over 4 sine phi into 2 pi minus 0 into d phi. Q enclosed equal to integral 0 to pi k r4 over 4 sine phi into 2 pi into d phi. Now we have only integral due to phi. So finally we integrate due to phi. Our q enclosed equal to q enclosed k r4 over 4 into 2 pi cos cos phi limit of integration from 0 to pi, and by applying limits q enclosed equal to k r4 over 4 2 pi minus cos pi minus cos 0 bracket close. So q enclosed equal to k r4 over 4 2 pi minus into minus 1 minus into minus 1. So Q enclosed equal to K or 4 over 4 2 pi into 2, and this will be equal to Q enclosed K or 4 over 4 into 4 pi. Here 4 cancel with 4, so our Q enclosed equal to K pi r 4. We call this equation number 3. Now we just put this equation into this equation, so we naming this equation as equation number 3 and this equation as equation number 4 by putting equation number 4 into 1. We get closed integral E dot dA is equal to K pi r4 over epsilon naught. Now as from figure, if we see from figure, E field due to this charge distribution is pointing radially outward, and if we consider here a small patch, then due to this patch area vector is also pointing radially outward, says dA. So from here you see that both are pointing radially outward and have theta equal to 0. So from this relation, if we take dot product of this quantity, we have this relation equal to close integral E dA cos of theta, and theta equal to 0. So this is equal to K pi r 4 over epsilon naught, and from here this will be equal to 1. So we have E close integral d of a K pi r 4 over epsilon naught. Here dA is a area of sphere that is equal to A equal to 4 pi r square. We just put this into this relation, so E into 4 pi r square equal to K pi r 4 over epsilon naught. So from here r square will cancel with r4 and we have r square here. So our E field equal to E is equal to 1 over 4 pi epsilon naught K pi r. And if we talk about vector form of this relation, then E vector equal to 1 over 4 pi epsilon naught K pi r into r unit vector, and this will be pointing radially outward.